Tonight, we drift through starlight, through ancient spirals and hidden depths, through a galaxy that holds us without asking, turns us without warning, and keeps secrets older than memory itself. Above you right now, even if clouds hide it, even if city lights drown it out, the Milky Way stretches across the darkness like a river of light. A pale band arcing overhead, soft and distant, whispering of depths we can barely fathom. But what you see is not what exists. That gentle glow is only the surface, the thinnest veil over mysteries that have taken a century to begin unraveling. Behind that familiar band lies a structure so vast, so strange, that even now, living within it, we struggle to map its true shape. The Milky Way is not just our home. It's a puzzle written in starlight, a question mark spiraling through the void. And tonight, as you close your eyes and let these words wash over you, we'll explore the secrets it's been keeping, one gentle revelation at a time. Before we begin, if you find peace in these quiet explorations, a gentle like or subscribe would mean everything. It's a small gesture, but it keeps this universe of bedtime stories alive, reminding me that somewhere, someone is listening, breathing, drifting alongside me through the cosmic dark. Now, let the stillness settle. Let your shoulders soften. And let's begin with the first secret, the one that took us centuries to discover. For thousands of years, humanity gazed at the Milky Way and saw only a river, a pale stream crossing the heavens, unchanging and eternal. Ancient Greeks called it Galaxius Kyklos, the Milky Circle. Roman poets saw it as spilled divine milk. Chinese astronomers named it the Silver River. But no one, not for millennia, understood what they were actually seeing. The truth is both humbling and beautiful. We live inside the galaxy, embedded so deeply in one of its spiral arms that for most of human history we couldn't see the forest for the trees. It's like trying to understand the shape of a city while standing in the middle of a crowded street. The perspective is limited, the view obscured by what's closest. The first person to glimpse the truth was William Herschel, a musician turned astronomer who, in the late 1700s, began counting stars. Night after night, using handmade telescopes, he mapped the positions of thousands of stars, trying to discern a pattern. What he found was that stars weren't evenly distributed. They formed a flattened disk, a structure with width and depth, but relatively thin height. But Herschel couldn't see the spiral. He saw only the disk, and even that was revolutionary. It wasn't until the 1920s that the full picture began to emerge. Edwin Hubble, working at Mount Wilson Observatory in California, was studying what astronomers then called spiral nebulae, those mysterious cloudy spirals scattered across the night sky. Using the 100-inch Hooker telescope, the largest in the world at that time, Hubble measured the distance to one of these spirals, the Andromeda Nebula. What he found changed everything. Andromeda wasn't a nebula within our galaxy. It was another galaxy entirely, millions of light years away. And if Andromeda was a spiral galaxy, vast and distant, then perhaps our own Milky Way was a spiral too. According to records from the Carnegie Observatories, Hubble's discovery in 1924 revealed that the universe was far larger than anyone had imagined, filled with countless galaxies, each a system of billions of stars. Our Milky Way was just one among multitudes. But confirming our galaxy's spiral shape took decades more. From inside the spiral, it's almost impossible to see the arms clearly. Dust and gas block our view, obscuring distant regions. Stars crowd the foreground. The perspective is skewed, the angle's wrong. Scientists had to piece it together slowly, like archaeologists reconstructing a vase from scattered fragments. They mapped the positions of young, bright stars, regions where new stars were forming. They traced the distribution of hydrogen gas using radio telescopes, which could peer through the dust, that blocked visible light. They measured distances, velocities, temperatures. NASA's Spitzer Space Telescope, launched in 2003, provided crucial data by observing in infrared light, which penetrates dust clouds more effectively than visible light. These observations revealed the structure of our spiral arms more clearly than ever before. The European Space Agency's Gaia mission, which began mapping the precise positions and motions of over 1 billion stars in 2013, added even more detail. What emerged from all this patient work was a portrait. A spiral galaxy, roughly 100,000 light-years across, with 4 major arms, or possibly 2 major arms and 2 minor ones, depending on how you count. The Milky Way rotates slowly, majestically, completing 1 full turn every 225 to 250 million years. Our Sun, nestled in a minor spur called the Orion Arm, rides along this rotation at about 514,000 miles per hour. Yet we feel nothing, no wind, no acceleration, no sense of movement. We are carried in perfect harmony with everything around us, locked in the galaxy's gentle, endless waltz. The realization that we live in a spiral, that the band of light overhead is our view from within one of those graceful arms, transforms how we see the night sky. Every star you can see with your naked eye is part of our local neighborhood, nearby points of light in the same spiral structure. The distant glow, that soft band, is the combined light of billions of stars farther along the arms, too distant to resolve individually. In a way, the Milky Way kept its shape secret simply by surrounding us. Only by looking outward, studying other galaxies, could we begin to understand our own. As the astrophysicist Harlow Shapley once reflected, we are not at the center of anything. We orbit in the outer regions, far from the core, in a quiet corner where stars are neither too dense nor too sparse. It's a modest location, unremarkable by galactic standards. And yet, from this quiet place, we've managed to map the structure that contains us. The spiral arms themselves are not permanent structures. They're density waves, regions where stars, gas, and dust temporarily bunch together as they orbit the galactic center. Think of them like traffic jams on a highway. The cars move through the jam, but the jam itself stays in roughly the same place. Stars pass through the spiral arms over millions of years, sometimes triggering bursts of star formation as gas clouds compress. This dynamic nature of spiral arms was first proposed by astronomers C.C. Lin and Frank Hsu in the 1960s. Their density wave theory explained why spiral patterns persist even though individual stars move at different speeds. The waves rotate more slowly than the stars themselves, creating the lasting pattern we observe. When a star or gas cloud enters a density wave, it slows down slightly due to the increased gravitational pull. This compression is what makes the spiral arms visible. Young, hot stars illuminate the arms, making them stand out against the background disk. These young stars don't live long enough to leave the spiral arms, which is why spiral arms appear blue in photographs of other galaxies, while the regions between appear yellower and redder. Our Sun sits in a small spur called the Orion Spur, or local arm, between 2 major arms. Our Sun passes through a spiral arm roughly every 100 million years. During these passages, the increased density of gas and dust may trigger meteor showers or even influence Earth's climate over geological timescales. The center of the galaxy, that bright bulge, is crowded with older stars, densely packed into a spherical region. Beyond the visible disk, astronomers have discovered globular clusters, ancient groups of hundreds of thousands of stars that orbit far above and below the disk, providing a 3-dimensional framework around the flat spiral. Take a breath. Feel the stillness. Right now, you are spinning through space at 500,000 miles per hour, carried by a spiral arm in a galaxy you can barely see from within. The Earth turns beneath you, the Sun orbits the galactic center, and the entire spiral sweeps through the universe's darkness. You are not still. You never have been. But the motion is so smooth, so perfectly synchronized, that it feels like peace. The mapping of the Milky Way continues. New telescopes reveal more details every year, building a complete picture of our home galaxy. One recent discovery involves the Milky Way's warp. The galactic disk isn't perfectly flat, but bends like the brim of a hat, possibly caused by gravitational interactions with satellite galaxies. Now, with that first secret revealed, another emerges. Because mapping the spiral was only the beginning, what scientists found at the galaxy's heart was far stranger than anyone expected. At the very heart of the Milky Way, hidden behind immense clouds of dust and gas, lies something that should not exist. A massive black hole, silent, invisible, and impossibly heavy. For decades, astronomers suspected it was there. Stars near the galactic center moved strangely, orbiting an empty point in space at speeds that defied explanation. Something unseen was pulling them, something with tremendous gravitational power. In the 1990s, two teams of astronomers began watching those central stars with extraordinary patience. Reinhard Genzel in Germany and Andrea Ghez in California independently tracked individual stars as they whipped around the galaxy's core, some completing orbits in just over a decade. What they discovered earned them the Nobel Prize in Physics in 2020. At the center of our galaxy sits a supermassive black hole with a mass 4 million times that of our Sun, compressed into a region smaller than our solar system. They named it Sagittarius A star, pronounced Sagittarius A star after the constellation where it resides. According to observations compiled by the European Southern Observatory's Very Large Telescope in Chile, this black hole is not just massive, it's surprisingly quiet. Despite its immense size, it's relatively inactive, consuming very little matter compared to black holes in other galaxies. But that doesn't mean it's harmless. Imagine the Sun, that brilliant burning sphere that warms our days, suddenly compressed into a point smaller than Earth. Then multiply its mass 4 million times. That's the scale of Sagittarius A star, a gravitational well so deep that nothing, not even light, can escape once it crosses the event horizon. The stars orbiting it move at a significant fraction of light speed. One of them, called S2, completes its orbit in just 16 years, swinging so close to the black hole that relativistic effects become visible. Time itself runs slower for S2 during its closest approach, exactly as Einstein's equations predicted. NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton satellite have detected faint X-ray emissions from the region around Sagittarius A star. These flares occur when small amounts of gas fall toward the black hole, heating to millions of degrees before disappearing forever beyond the event horizon. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A. Not the black hole itself, which emits no light, but the glowing ring of superheated matter swirling around it. The image showed a dark circle, the shadow of the black hole, surrounded by a luminous halo of doomed gas and dust. It was the second black hole ever photographed and the first image of the monster at our own galaxy's heart. What makes this discovery so profound is the realization that supermassive black holes appear to exist at the center of nearly every large galaxy. They're not rare cosmic accidents, but fundamental components of galactic structure. Some astronomers believe these black holes actually help shape their host galaxies, their gravity guiding the formation of stars and spiral arms. The Milky Way's central black hole may have been growing for billions of years, fed by gas, dust, and the occasional star that wandered too close. Yet, for all its mass, It's relatively small compared to black holes in some other galaxies. The black hole at the center of M87, for instance, is over 6 billion times the mass of the Sun, more than 1,000 times heavier than our own. Why some black holes grow so much larger remains a mystery. It may depend on how much matter was available in the early universe, how many galaxy mergers occurred, or simply how long the black hole has been feeding. What we do know is that Sagittarius A star is remarkably quiet now. It's not actively devouring large quantities of matter. Instead, it sits dormant, sipping only small amounts of gas that drift too close. But it wasn't always this calm. Evidence from X-ray observations suggests that a few million years ago, just a blink of cosmic time, the black hole underwent a period of intense activity. It may have consumed a large gas cloud or torn apart a star, producing a burst of radiation that lit up the galactic center like a beacon. Those ancient photons are still traveling outward, and when they strike distant gas clouds, they cause them to glow faintly, creating what astronomers call light echoes. The Fermi Gamma Ray Space Telescope has detected these echoes, structures called the Fermi bubbles, enormous lobes of high-energy radiation extending 25,000 light-years above and below the galactic plane. These bubbles are evidence of a violent past, a time when our galaxy's heart was not sleeping but blazing with energy. And it could wake again. If a large gas cloud or a wayward star wanders too close, Sagittarius A star could roar back to life, releasing jets of radiation that would light up the galaxy's core. We wouldn't be in danger, we're far too distant, 26,000 light-years away, but the sky would change. Our ancestors might see the galactic center glow brighter, a new beacon in the night. For now, though, the black hole waits. Patient, silent, and impossibly heavy, it anchors our galaxy, holding the central stars in their frantic orbits, shaping the flow of matter and energy around it. The region immediately surrounding Sagittarius A is one of the most extreme environments in the galaxy. The density of stars there is millions of times higher than in our solar neighborhood. Stars pass within light days of each other, close enough that gravitational interactions are common. Some stars are flung outward at incredible speeds, becoming hypervelocity stars that escape the galaxy entirely. Others spiral inward, eventually crossing the event horizon and disappearing forever. One particularly fascinating object near the galactic center is G2, a dusty gas cloud about 3 times Earth's mass. In 2014, it passed within just a few light hours of Sagittarius A, close enough that astronomers expected it to be torn apart and consumed, potentially triggering a burst of X-ray emission. But G2 survived the encounter largely intact, suggesting it might not be a simple gas cloud, but a young star shrouded in dust. The nature of G2 remains uncertain, but its survival demonstrates how resilient some objects can be, even in the extreme environment near a supermassive black hole. Around the galactic center, within a region about 1 light-year across, astronomers have identified a cluster of massive young stars. These stars, some weighing more than 100 times the Sun's mass, are puzzling. The tidal forces near the black hole should prevent star formation in this region. How these massive stars came to be so close to Sagittarius A remains an open question. One theory suggests they formed farther out and migrated inward through gravitational interactions. Another proposes they formed in a massive disk of gas that briefly existed around the black hole millions of years ago. The truth may be some combination of these scenarios or something else entirely. The black hole itself is invisible, but its influence extends far beyond the immediate vicinity. It shapes the orbits of stars thousands of light-years away, creates density waves in the surrounding gas, and may have played a role in forming the galactic bulge itself. Some models suggest that in the early universe, supermassive black holes formed before galaxies, seeding the regions where galaxies would eventually coalesce. In this view, the black hole came first, and the galaxy grew around it. Other models suggest the opposite, that galaxies formed first and black holes grew within them. The truth probably lies somewhere in between, with black holes and galaxies co-evolving, each influencing the other's growth. What's clear is that the relationship between a galaxy and its central black hole is intimate. Observations of other galaxies show a tight correlation between black hole mass and the properties of the galactic bulge. Larger bulges have more massive black holes, a relationship that holds across a wide range of galaxy sizes and types. This correlation suggests a deep connection, a feedback mechanism where the black hole's growth affects the galaxy and the galaxy's evolution affects the black hole. When a black hole feeds actively, it releases enormous amounts of energy, heating the surrounding gas and blowing it away. This can shut down star formation in the central regions of a galaxy, regulating its growth. Over billions of years, this feedback may explain why supermassive black holes don't grow indefinitely. They reach a size where their energy output prevents more matter from falling in, creating a natural equilibrium. Take a slow breath. Right now, while you rest, that black hole sits at the center of everything, invisible and inescapable. Not a threat, but a foundation. A secret so massive, it shapes the galaxy, yet so hidden, we only recently confirmed it exists. In the coming decades, new instruments will probe the galactic center in even greater detail. The Event Horizon Telescope continues to improve, adding more telescopes to its global network and increasing its sensitivity. Future observations may reveal the black hole's spin rate, its magnetic field structure, and the dynamics of matter spiraling toward the event horizon. NASA and the European Space Agency are planning next-generation X-ray observatories that will study the hot gas around Sagittarius A with unprecedented precision. These missions may catch the black hole in a more active state, revealing how it feeds and how its energy output affects the surrounding environment. And as we drift outward from that dark heart, we find that the galaxy holds even stranger secrets, hidden not at the center, but scattered throughout its spiral arms. Mysteries written in starlight and shadow, waiting for us to decipher them. The galaxy is eating its neighbors. The Milky Way seems peaceful, majestic, a slow spiral of starlight rotating through the cosmic dark. But it's also a cannibal. Right now, as you lie here in stillness, our galaxy is actively consuming smaller galaxies, tearing them apart star by star, absorbing their matter into our own spiral structure. This isn't speculation. It's documented, measured, and ongoing. Astronomers have discovered dozens of stellar streams, long rivers of stars stretching across the sky. Each one the scattered remains of a dwarf galaxy that wandered too close to the Milky Way and was pulled apart by tidal forces. The European Space Agency's Gaia mission has been crucial in uncovering these streams. By precisely measuring the positions and velocities of over 1 billion stars, Gaia revealed that many stars in our galaxy are moving in coordinated groups, following paths that trace back to ancient collisions. One of the most significant discoveries was the Gaia Enceladus stream, the remnant of a dwarf galaxy that merged with the Milky Way about 10 billion years ago. This collision was violent enough to heat up our galaxy's disk and may have triggered a burst of star formation. According to research published by astronomers at the University of Cambridge, Gaia Enceladus contained roughly 600 million times the mass of the Sun before it was consumed. Today, its stars are scattered throughout the Milky Way's halo, no longer a distinct galaxy, but part of our own. But the Milky Way didn't stop there. It's still feeding. The Sagittarius dwarf elliptical galaxy is currently being torn apart. Located on the opposite side of the galaxy from us, this small galaxy has already made several passes through the Milky Way's disk, each time losing more stars and gas. NASA's observations show that streams of stars from Sagittarius stretch completely around our galaxy, wrapped like ribbons around a gift. In another few billion years, Sagittarius will be completely dissolved, its stars fully integrated into our spiral structure. It will cease to exist as a separate entity. Then there's the Large and Small Magellanic Clouds, two small companion galaxies visible to the naked eye from the southern hemisphere. They orbit the Milky Way, slowly spiraling inward. Eventually, they too will merge with us, adding their stars to our spiral arms. In fact, recent studies using data from the Hubble Space Telescope and Gaia suggest that the Magellanic Clouds may already be losing gas and stars to the Milky Way's gravitational pull. A vast stream of hydrogen gas, called the Magellanic Stream, trails behind them like a comet's tail, stretching across more than half the southern sky. This stream was discovered in the 1970s through radio telescope observations. It contains enough gas to form millions of stars, material that will eventually rain down onto the Milky Way's disk, fueling future generations of star formation. The Magellanic Clouds themselves are fascinating objects. The Large Magellanic Cloud contains about 10 billion stars, making it a substantial dwarf galaxy. The Small Magellanic Cloud is smaller, with perhaps a few billion stars. Both are irregular in shape, lacking the spiral or elliptical structure of larger galaxies. They orbit the Milky Way roughly once every 1.5 billion years, though their orbits are complex and influenced by their mutual gravitational interaction as well as the Milky Way's pull. Recent measurements suggest they may be on their first close approach to our galaxy, having fallen inward from the outskirts of the local group. If so, their eventual merger with the Milky Way is still billions of years in the future, but the process has already begun. The Magellanic Stream is evidence that the Milky Way's gravity is strong enough to strip gas from these companions even at their current distance. This process of galactic cannibalism is not unique to the Milky Way. It's common throughout the universe. Large galaxies grow by consuming smaller ones, a cosmic hierarchy of gravity and time. Computer simulations run by astronomers at institutions like NASA's Goddard Space Flight Center show that our galaxy has likely absorbed dozens of smaller galaxies over its lifetime. Each merger adds mass, changes the distribution of stars, and can trigger new waves of star formation as gas clouds collide and compress. In a sense, the Milky Way is not a single, pure entity. It's a composite, a patchwork quilt woven from the remnants of many smaller galaxies. Some of the stars in our night sky may have formed in galaxies that no longer exist, their original homes dissolved into our own. Even our sun might be a second-generation immigrant. Some theories suggest that the sun formed from gas enriched by previous generations of stars, possibly including material from dwarf galaxies consumed billions of years ago. The idea is both unsettling and beautiful. We are not just citizens of the Milky Way. We are the descendants of lost galaxies, children of structures that no longer have names. And the cannibalism continues. The Milky Way's gravity reaches far beyond its visible disk, extending into a massive dark matter halo that encompasses satellite galaxies and stellar streams. Anything that wanders into this gravitational web eventually succumbs, stretched and torn by tidal forces until it becomes part of the larger structure. This ongoing consumption is one way galaxies grow. The Milky Way was once smaller, perhaps just a fraction of its current size. Over billions of years, it has grown through mergers, each collision adding new stars, gas, and dark matter. But there's a limit to this growth. Because the Milky Way itself is not the final predator, something larger is approaching. In about 4.5 billion years, our galaxy will collide with Andromeda, the nearest large spiral galaxy. This merger will be spectacular, a cosmic dance spanning millions of years as the two galaxies pass through each other, their stars rarely colliding, but their structures completely disrupted. Simulations created by astronomers using supercomputers show that the Milky Way and Andromeda will merge into a single giant elliptical galaxy, sometimes playfully called Milkomeda. The spiral arms will dissolve, stars redistributed into a more rounded, diffuse shape. By that time, our Sun will be nearing the end of its life anyway, swelling into a red giant. Humanity, if it still exists, will have long since abandoned Earth or evolved beyond recognition. But the galaxy that gave birth to us will also transform, losing its spiral beauty to become something new. For now, though, the Milky Way remains a spiral, still feeding, still growing, still beautiful. A cannibal wrapped in starlight, devouring its neighbors with patience and grace. The evidence of past mergers is written throughout the galaxy's structure. The thick disk, a layer of older stars above and below the thin disk where most star formation occurs, may have been created by ancient collisions. The stellar halo, containing old stars and globular clusters in orbits that take them far from the galactic plane, is thought to be composed largely of material from consumed dwarf galaxies. Even the chemical composition of stars provides clues. Stars born in dwarf galaxies often have different ratios of heavy elements compared to stars born in the Milky Way's disk. By analyzing stellar spectra, astronomers can identify stars that likely originated in other galaxies and trace their orbits back to estimate when their parent galaxy was consumed. One particularly intriguing discovery is a group of stars called the Helmy stream, named after astronomer Amina Helmy, who identified it. These stars orbit the galaxy in a coordinated fashion, suggesting they came from a single dwarf galaxy that merged with the Milky Way several billion years ago. Chemical analysis of these stars reveals they have lower metallicity than typical Milky Way stars, consistent with formation in a smaller, less evolved galaxy. The process of identifying these ancient merger events has become a major field of galactic archaeology. By studying the motions, ages, and chemical compositions of stars, astronomers can reconstruct the Milky Way's violent history, identifying when and where past collisions occurred. Each merger leaves a distinctive signature. When a dwarf galaxy falls into the Milky Way, its stars are scattered along its orbital path, creating a stream that stretches around the galaxy. These streams gradually disperse over time as stars drift apart, but for several billion years, they remain identifiable as coherent structures. The Sagittarius stream is the most dramatic example. This stream completely encircles the Milky Way, wrapping around it multiple times like thread wound around a spool. The multiple wraps indicate that the Sagittarius dwarf has already completed several orbits through our galaxy, each passage stripping away more material. The stream is not uniform. Some regions are denser than others, corresponding to the current location of the dwarf galaxy's core and the locations where it passed through the disk on previous orbits. By mapping these density variations, astronomers can reconstruct the dwarf galaxy's orbital history. What makes these tidal streams especially valuable is that they're sensitive traces of the Milky Way's gravitational field, including the distribution of dark matter. The precise shape of a stream depends on the exact gravitational forces acting on it. So by measuring stream positions and velocities, astronomers can infer properties of the dark matter halo. This has revealed that the Milky Way's dark matter halo is not perfectly smooth. It has substructure, lumps and clumps left over from smaller dark matter halos that merged with our galaxy in the past. These dark matter subhalos can perturb stellar streams, creating gaps and kinks that help astronomers map the invisible mass distribution. The study of stellar streams has also revealed unexpected complexity. Some streams appear to have been perturbed by something massive passing nearby, creating waves and gaps in the stream. The perturber, might be a dark matter subhalo, too faint to see directly, but massive enough to gravitationally disturb passing stars. Alternatively, the perturbations might come from the Milky Way's spiral arms. As the density waves rotate through the galaxy, they can gravitationally nudge stars in tidal streams, creating patterns that encode information about the spiral structure's strength and rotation speed. Take a quiet breath. You are part of this ancient process, built from atoms forged in stars that may have belonged to other galaxies once. The iron in your blood, the calcium in your bones, they could be immigrants from lost worlds, merged long ago into the spiral that holds you now. The future holds more mergers. Besides the Magellanic Clouds and the eventual collision with Andromeda, the Milky Way will likely consume several smaller satellite galaxies over the coming billions of years. Currently, astronomers have identified about 50 satellite galaxies orbiting the Milky Way, ranging from relatively large systems like the Magellanic Clouds down to ultra-faint dwarfs containing just a few thousand stars. Many of these satellites are on trajectories that will eventually bring them into the Milky Way's disk. When they arrive, they'll be torn apart, their stars scattered, their identities erased. They'll become part of us, just as we are part of galaxies that were consumed in the past. This cycle of destruction and renewal is fundamental to galactic evolution. Galaxies don't grow in isolation. They grow through mergers, each collision reshaping structure and adding fresh material to the cosmic mix. What's remarkable is how these mergers trigger creation. When gas clouds from two galaxies collide, they compress, heat, and trigger massive bursts of star formation. Some of the most spectacular starburst galaxies in the universe are systems caught in the act of merging. Our own merger with Andromeda will likely produce similar fireworks. Though the event is 4.5 billion years away, computer simulations show the galaxies will slide through each other multiple times over about 2 billion years, each passage stripping away energy until they finally merge into a single giant elliptical galaxy, erasing both spirals completely. The study of galactic cannibalism has implications beyond understanding the Milky Way's history. It provides insights into how galaxies evolve throughout the universe. Observations of distant galaxies show that mergers were more common in the early universe when galaxies were closer together and gravitational interactions more frequent. Today, in our cosmic neighborhood, major mergers are rare. But minor mergers, the consumption of dwarf galaxies by larger ones, continue at a steady pace. The Milky Way may currently have dozens of small satellite galaxies, though most are so faint they're difficult to detect. Each one is a potential future meal destined to be absorbed over the coming billions of years. And as we drift deeper into the galaxy's secrets, we encounter a mystery that challenges everything we thought we knew about matter itself. Because most of what holds this galaxy together isn't made of stars or gas or dust. It's something far stranger, something we still cannot see or touch. If you could weigh the Milky Way, counting every star, every planet, every cloud of gas and dust, you'd find something deeply troubling. The numbers wouldn't add up. All the visible matter, everything that shines or glows or reflects light, accounts for less than 15% of the galaxy's total mass. The rest, roughly 85%, is completely invisible. It doesn't emit light, doesn't absorb it, doesn't interact with electromagnetic radiation in any way we can detect. Astronomers call it dark matter, and it's everywhere, woven throughout the galaxy like an invisible web, holding everything together with its gravity alone. The first hints of this mystery appeared in the 1930s when Swiss astrophysicist Fritz Zwicky studied galaxy clusters. He measured how fast galaxies were moving within the cluster and realized they were moving too fast. The visible matter wasn't generating enough gravity to hold them together. They should have flown apart long ago. Zwicky proposed that unseen matter must be present, providing the additional gravity. He called it dunkel materie, dark matter. But his idea was largely ignored for decades. Then in the 1970s, American astronomer Vera Rubin made a discovery that couldn't be dismissed. She measured the rotation speeds of spiral galaxies and found that stars on the outer edges were moving just as fast as stars near the center. This violated everything physicists understood about orbital mechanics. According to Newton's laws and Einstein's relativity, objects farther from a gravitational center should move slower, like planets in our solar system, Mercury orbiting faster than Neptune. But in galaxies, the rotation curve stayed flat. Stars at the edge moved impossibly fast. The only explanation was that galaxies are embedded in massive halos of invisible matter, extending far beyond their visible disks. This dark matter provides the extra gravity needed to keep those outer stars from flying away. NASA's observations confirm that our Milky Way is no exception. Models based on the motions of stars and satellite galaxies suggest that our galaxy sits within a dark matter halo, stretching perhaps 600,000 light-years across, far larger than the visible spiral. This halo contains roughly 10 times as much mass as all the stars, gas, and dust combined. It's the gravitational foundation upon which the galaxy rests. But what is dark matter made of? No one knows. It's not ordinary matter, atoms and molecules. If it were, we'd see it absorbing or emitting light somewhere on the electromagnetic spectrum. It's not black holes, because we detect their gravitational lensing effects. It's not dust or gas, because those scatter light. Whatever it is, it interacts with normal matter only through gravity. It doesn't collide, doesn't clump, doesn't form structures the way ordinary matter does. The leading candidates are theoretical particles such as WIMPs, weakly interacting massive particles, or axions, even more exotic and lightweight particles. Experiments around the world, deep underground to shield them from cosmic rays, are searching for these particles. So far, none have been detected with certainty. The European Space Agency's Euclid mission, launched in 2023, is mapping the distribution of dark matter across the universe by observing how it bends light from distant galaxies. NASA's upcoming Nancy Grace Roman Space Telescope will continue this work, creating detailed maps of dark matter's gravitational influence. What these missions reveal is that dark matter isn't evenly distributed. It forms filaments, vast cosmic webs connecting galaxy clusters. Galaxies like the Milky Way form where these filaments intersect, where dark matter's gravity is strongest. In a way, visible matter is just decoration, condensing along the scaffolding that dark matter provides. Without dark matter, galaxies couldn't form, stars wouldn't cluster. The universe would look completely different, perhaps devoid of the structures that make life possible. Computer simulations run by teams at institutions like the Max Planck Institute for Astrophysics show that dark matter halos are essential for galaxy formation. In simulations without dark matter, galaxies tear themselves apart, unable to hold together against their own rotation. So the Milky Way, this beautiful spiral we call home, is really just a small visible component of a much larger, invisible structure. The stars we see are like foam on the surface of a dark ocean, supported by depths we cannot perceive. This realization is humbling. For all our technology, for all our telescopes and equations, we still cannot identify what most of the universe is made of. We can measure its effects, map its distribution, but we cannot see it or touch it. It's as if the galaxy is a house where 85% of the rooms are locked, and we can only peek through keyholes, inferring what's inside by the shadows on the walls. Dark matter may also hold clues to the galaxy's history. The way it's distributed, the structure of its halo, tells us about ancient collisions and mergers. Some astronomers believe they can identify streams of dark matter, remnants of smaller dark matter, halos from dwarf galaxies that were consumed. These streams, if detected, would be like archaeological layers, records of the Milky Way's growth over billions of years. The James Webb Space Telescope, with its incredible sensitivity, is helping astronomers study the earliest galaxies in the universe. By observing how these ancient galaxies formed and evolved, scientists hope to understand the role dark matter played in shaping cosmic structure. Every observation points to the same conclusion: dark matter is not just a curiosity, it's fundamental. Without it, galaxies wouldn't exist, stars wouldn't form. And life, emerging on a small planet orbiting an ordinary star, would never have had the chance to look up and wonder at the darkness between the lights. The search for dark matter particles continues in laboratories around the world. Deep underground, shielded from cosmic rays that could create false signals, detectors wait for the rare collision of a dark matter particle with ordinary matter. These experiments use ultra-pure materials, cooled to near absolute zero, monitored by exquisitely sensitive instruments. The idea is simple. If dark matter particles exist and pass through ordinary matter, occasionally one should collide with an atomic nucleus, creating a tiny burst of energy. By detecting these rare collisions, scientists hope to identify the particle responsible for dark matter. But decades of searching have yielded no confirmed detections. Either dark matter particles interact even more weakly than expected, or they're not particles at all but something stranger, perhaps a modification to the laws of gravity itself. Some physicists have proposed alternatives to dark matter, theories that modify Newton's and Einstein's equations to explain galaxy rotation without invoking invisible mass. The most well-known is modified Newtonian dynamics, or MOND, which suggests that gravity behaves differently at very low accelerations. MOND can explain the flat rotation curves of galaxies without dark matter, but it struggles to account for other observations, like the behavior of galaxy clusters and the cosmic microwave background radiation. Most physicists believe dark matter remains the best explanation, even if we haven't yet identified what it is. Take a breath. Right now, you're surrounded by dark matter. It's passing through you, through the Earth, through the walls of your room. Countless particles, if that's what they are, moving silently through ordinary matter like ghosts through walls. You can't feel them, you can't see them, but their gravity shapes the galaxy that holds you, the stars that light your nights, the planet that gives you ground to stand on. Most of the galaxy is missing, but in a way, that mystery makes it more beautiful, because it means there's still so much to discover, still depths we haven't plumbed, still secrets the Milky Way keeps close. The existence of dark matter also raises profound questions about the nature of reality. If most of the universe is made of something we cannot directly perceive, what does that say about our place in it? Are we living in a thin layer of ordinary matter, floating on an ocean of dark matter we can never fully understand? Or will future generations develop new instruments, new theories, new ways of perceiving the universe that make dark matter as obvious and measurable as starlight is to us today? The answer remains to be discovered. But the search continues, driven by curiosity and the knowledge that understanding dark matter means understanding the very foundation of cosmic structure. And speaking of secrets, there's one more that stretches across the galaxy's arms, hidden in plain sight, yet invisible to the naked eye. A structure so vast it took decades to map, and even now, we're not sure we understand its purpose. Between the stars, in the vast spaces we think of as empty, there exists a network, a web of gas and magnetic fields stretching across the galaxy like arteries in a living body. Astronomers call it the interstellar medium, the ISM, and it's far from empty. This medium fills the gaps between stars with hydrogen gas, helium, trace elements, and dust grains so fine they're measured in microns. It's incredibly diffuse, far more tenuous than any vacuum we can create on Earth, yet it contains roughly 10 to 15% of the galaxy's visible mass. More importantly, it's the material from which new stars are born. The ISM exists in different states, different temperatures and densities. Cold molecular clouds, where temperatures drop to just 10 degrees above absolute zero, are the densest regions, where gravity can pull gas together to form stars. Warm regions, heated by nearby stars, glow faintly in radio and infrared wavelengths. Hot regions, blasted by supernova explosions, shine in X-rays. NASA's Spitzer Space Telescope and the European Space Agency's Herschel Space Observatory have mapped these regions in detail, revealing a complex, dynamic structure constantly in motion. But there's more to the ISM than just gas and dust. It's threaded with magnetic fields, invisible lines of force that stretch across light years, guiding the flow of charged particles and shaping the formation of new stars. These magnetic fields were discovered through observations of starlight. As light passes through dust grains aligned by magnetic fields, it becomes slightly polarized, twisted in a specific direction. By measuring this polarization across the sky, astronomers can map the orientation of magnetic fields throughout the galaxy. What they've found is astonishing. The magnetic fields aren't random. They follow the spiral arms, reinforcing the galaxy's structure. They help regulate star formation by supporting gas clouds against gravitational collapse, at least until those clouds become dense enough that gravity wins. According to research from institutions like the Max Planck Institute for Radio Astronomy, these magnetic fields may play a crucial role in galactic dynamics, influencing everything from the birth of stars to the propagation of cosmic rays. But the ISM isn't static. It's constantly being churned, heated, and recycled by stellar processes. When massive stars die in supernova explosions, they blast gas and dust back into the ISM, enriching it with heavier elements forged in stellar cores. This material eventually cools, condenses, and forms new stars and planets. The atoms in your body were once part of this interstellar medium, cycled through multiple generations of stars before condensing onto a planet where life could emerge. The ISM also contains cosmic rays, high-energy particles accelerated to nearly the speed of light by supernova shockwaves and other violent processes. These particles stream through the galaxy, passing through you right now, thousands per second, unnoticed. Cosmic rays play a crucial role in galactic chemistry. When they collide with molecules in the interstellar medium, they trigger reactions that help form complex organic compounds in molecular clouds. The amino acid precursors, the alcohols, the complex carbon chains detected in space all owe part of their existence to these energetic particles. The galaxy's magnetic field, threaded through the ISM, acts as a highway for cosmic rays and helps regulate star formation. Magnetic fields can extract energy from the disk, drive galactic winds, and channel hot gas from supernova explosions into the halo, creating the galactic fountain that cycles material between disk and halo. NASA's Voyager 1 spacecraft, beyond the Sun's protective bubble, has been measuring the interstellar medium directly. The data reveals that the interstellar magnetic field is stronger than expected and the density higher, meaning our solar system sits in a relatively dense region of local space. Recently, astronomers have discovered enormous structures within the ISM called superbubbles, cavities hundreds of light years across, carved out by multiple supernova explosions. These bubbles are bounded by shells of compressed gas, glowing faintly in radio and X-ray wavelengths. The Fermi bubbles, those vast lobes of gamma-ray emission extending above and below the galactic center, may be related to superbubbles, perhaps inflated by a burst of activity from the central black hole millions of years ago. The galaxy's invisible skeleton, this network of gas, dust, and magnetic fields, is what gives the Milky Way its structure. The spiral arms we explored at the beginning aren't just collections of stars, they're regions where this invisible skeleton compresses, creating those density waves that trigger star formation. The stars are born, live briefly in cosmic terms, and die, returning their material to the ISM to begin the cycle again. In this way, the galaxy is alive, constantly renewing itself. It's not a static sculpture, but a dynamic system, a cosmic ecosystem where matter flows from gas to stars and back again. The ISM also contains molecules, complex organic compounds floating in the darkness between stars. Radio telescopes have detected over 200 different molecules in interstellar space, including water, ammonia, alcohols, and even amino acids, the building blocks of proteins. These discoveries, made by instruments like the ALMA Observatory in Chile, suggest that the chemistry of life may begin long before planets form. The raw ingredients are already present in the interstellar medium, waiting to be incorporated into new solar systems. When our Sun formed 4.6 billion years ago, it condensed from a cloud of gas and dust that was already enriched with these molecules. The complex organic chemistry we discovered floating in that invisible skeleton between the stars, those amino acids and water molecules, they were waiting there in the solar nebula. The Earth, the oceans, the first organic molecules that led to life, all inherited their chemistry from that primordial cloud. In a very real sense, the galaxy's invisible skeleton is also the framework of life. It's the source of raw materials, the nursery of stars, the reservoir of atoms that will one day become planets, oceans, and consciousness. The molecular clouds where stars form are among the coldest, densest regions of the ISM. These clouds can span hundreds of light years and contain enough material to form thousands or even millions of stars. They're called molecular because at these low temperatures, hydrogen atoms combine to form molecular hydrogen, H2. Molecular hydrogen is difficult to detect directly because it doesn't emit radio waves at the cold temperatures found in these clouds. Instead, astronomers trace molecular clouds using other molecules, particularly carbon monoxide, which emits radio waves more readily and is thought to be well mixed with hydrogen. The most famous molecular cloud is probably the Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword. This cloud is actively forming stars, and telescopes have revealed hundreds of young stars embedded within it, some still surrounded by protoplanetary disks where planets are forming. The Orion Nebula is relatively close, only about 1,300 light-years away, making it an ideal laboratory for studying star formation. Observations across multiple wavelengths reveal the complex processes at work: gas collapsing under gravity, magnetic fields channeling material, jets of matter erupting from young stars, and ultraviolet radiation from the hottest newborn stars gradually eroding the cloud that gave birth to them. Eventually, the cloud will be completely dispersed, leaving behind a cluster of young stars that will slowly drift apart over millions of years. This is the fate of all molecular clouds, to give birth to stars and then be destroyed by the very stars they created. Take a slow breath. Between you and the nearest star, there's not emptiness, but a faint mist of hydrogen, a whisper of dust, magnetic threads too subtle to see. That mist, that invisible web, connects you to the larger galaxy. It's where you came from and where your atoms will eventually return. The study of the interstellar medium has revealed that the galaxy is far more dynamic than once thought. Gas doesn't simply sit between the stars, it flows, circulates, and cycles through different phases. Hot gas from supernova explosions rises above the galactic disk, cools, and rains back down as cold clouds that can form new stars. This process, called the galactic fountain, helps distribute heavy elements throughout the galaxy. Without the galactic fountain, elements forged in stars near the galactic center would stay there, unable to reach the outer regions where our Sun formed. The presence of heavy elements in the Sun and Earth is evidence that this circulation has been operating for billions of years, mixing material from across the galaxy. The interstellar medium also interacts with the galaxy's magnetic field in complex ways. Charged particles, primarily electrons and protons from cosmic rays, spiral along magnetic field lines, creating a pressure that helps support the ISM against gravitational collapse. This magnetic pressure is comparable to thermal pressure in some regions, making magnetic fields an important component of the ISM's physics. Recent observations using instruments like the Planck satellite have mapped the magnetic field structure across the entire galaxy, revealing that the fields are stronger and more ordered than previously thought. This has implications for star formation, as strong magnetic fields can either inhibit or channel the collapse of gas clouds depending on their orientation. The Milky Way's secrets are layered, each discovery revealing new depths. From its spiral structure to its dark heart, from its cannibalistic growth to its invisible mass, and now this skeleton of gas and fields that binds it all together. And that invisible skeleton? It's not just structure, it's memory. Every atom in you carries the signature of a star that died before the Sun was born. But there's one secret left, perhaps the most profound, a question that brings us back to where we started, to the meaning of our place within this vast spiral. The Milky Way contains somewhere between 100 and 400 billion stars. Most of those stars have planets. And many of those planets exist in the habitable zone, the region where liquid water can exist on a surface. Given those numbers, the question isn't whether life exists elsewhere in the galaxy. The question is why we haven't heard from it. This paradox, first articulated by physicist Enrico Fermi in 1950, has haunted astronomers ever since. If the galaxy is so vast, so old, so full of potentially habitable worlds, where is everyone? NASA's Kepler Space Telescope, which operated from 2009 to 2018, revolutionized our understanding of planetary systems. It discovered over 2,700 confirmed exoplanets and revealed that planets are common, not rare. Nearly every star has at least one planet. Many have multiple planets, and a significant fraction of those worlds orbit in the habitable zone. Estimates suggest there may be tens of billions of Earth-like planets in the Milky Way alone. So, statistically, we should not be alone. Yet the galaxy is silent. Decades of searching for radio signals, for optical beacons, for any sign of technological civilization have turned up nothing. SETI, the search for extraterrestrial intelligence, has been listening since the 1960s, scanning millions of frequencies, analyzing billions of signals. So far, every potential detection has been explained by natural phenomena or human interference. No confirmed signal from another civilization has ever been received. This silence is one of the galaxy's deepest secrets. Because it suggests something profound, either life is extraordinarily rare, or intelligent civilizations don't last long, or they're hiding, staying quiet for reasons we don't understand. Some scientists propose the rare Earth hypothesis, the idea that while simple life might be common, complex life requires such a precise set of conditions that it's vanishingly unlikely. A stable star, a planet with the right mass and composition, a large moon to stabilize its axis, a protective magnetic field, a history free from catastrophic asteroid impacts, all these factors might need to align. Others suggest the Great Filter, a barrier that most civilizations fail to pass. Perhaps the jump from single-celled life to multicellular life is incredibly difficult. Or perhaps technological civilizations inevitably destroy themselves before they can spread across the stars through war, environmental collapse, or existential risks we haven't even imagined yet. Then there's the zoo hypothesis, the idea that advanced civilizations know we're here but choose not to interact, observing us from a distance like researchers studying uncontacted tribes. Or perhaps they communicate in ways we haven't learned to detect yet, using neutrinos, gravitational waves, or quantum entanglement instead of radio waves. NASA's James Webb Space Telescope is beginning to analyze the atmospheres of exoplanets, searching for biosignatures, chemical combinations like oxygen and methane together that would suggest biological processes. If JWST detects such signatures, it won't prove intelligent life, but it will confirm that life exists beyond Earth. That alone would be revolutionary. The European Space Agency's Plato mission, planned for launch in the coming years, will search for Earth-like planets around Sun-like stars, expanding our catalogue of worlds where life might exist. But even if we find evidence of life, even simple microbial life, it doesn't answer Fermi's paradox. Because the question isn't about life, it's about intelligence, about technology, about why no one is calling. Perhaps the answer is time. The galaxy is 13 billion years old. Civilizations may rise and fall over thousands or millions of years, tiny flickers in cosmic time. Two civilizations might exist in the galaxy at the same moment, but be separated by such vast distances that their signals never overlap. The speed of light is fast, but the galaxy is vast. A radio signal from a civilization 50,000 light-years away would take 50,000 years to reach us. By the time it arrives, that civilization might be long extinct. We might be listening for voices that went silent millennia ago. Or we might be early. Perhaps the Milky Way is just now reaching the stage where complex life and civilizations emerge. Perhaps we're among the first, not the last. That possibility is both exciting and lonely. If we're early, then the galaxy's future might be shaped by choices humanity makes in the coming centuries. We could be the predecessors, the ancient ones that future civilizations will wonder about. But there's also the possibility that life is common. Civilizations are common, but they all face the same challenge: survival. Perhaps every intelligent species reaches a point where technology gives them the power to destroy themselves, and only a few navigate that transition successfully. If that's the case, then the silence isn't a mystery, it's a warning. The galaxy may be full of ruins, dead worlds where civilizations flourished briefly before collapsing. Planets where life evolved, built cities, reached for the stars, and then fell silent. We have no way to know, not yet. What we do know is that Earth's biosphere is fragile, that our climate is changing, that we're developing technologies, artificial intelligence, genetic engineering, nuclear weapons, that could either elevate us or end us. The galaxy's silence might be asking us a question. Not where is everyone, but will you survive? As astronomer Carl Sagan reflected, we are a way for the cosmos to know itself. Perhaps the rarity isn't life, but self-awareness, the ability to look up, understand what we're seeing, and ask why we're alone. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicative civilizations in the galaxy. It multiplies factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, and so on, ending with the average lifetime of a technological civilization. The problem is that many of these factors are highly uncertain. We now have good estimates for the first few factors, thanks to missions like Kepler. But the later factors, particularly the probability that life develops intelligence and the average lifetime of civilizations are complete unknowns. Depending on the values you choose, the Drake equation can predict anything from thousands of civilizations in the galaxy to us being utterly alone. Recent discoveries have refined some of these factors. We now know that potentially habitable planets are common. We're beginning to understand the conditions necessary for life. But we still have no idea how often life arises, how often it develops intelligence, or how long civilizations last. The search for extraterrestrial intelligence continues through projects like Breakthrough Listen, funded by private donations and using some of the world's most powerful telescopes. These searches scan millions of stars, looking for narrow-band radio signals or laser pulses that could only be artificial. So far, nothing conclusive has been found. But the search has only examined a tiny fraction of the sky, at a limited range of frequencies for brief periods. It's like dipping a cup into the ocean and concluding there are no fish. A more comprehensive search will take decades, using next-generation radio telescopes like the Square Kilometre Array, currently under construction in South Africa and Australia. This array will be 50 times more sensitive than any existing radio telescope, capable of detecting weak signals from thousands of light-years away. There's also the possibility of detecting technosignatures, signs of advanced technology that aren't deliberate signals. These might include waste heat from massive energy consumption, atmospheric pollution from industrial activity, or even megastructures like Dyson spheres, hypothetical constructs that surround stars to capture their energy. NASA has begun funding research into technosignatures, recognizing that they might be more detectable than deliberate transmissions. After all, civilizations might broadcast for only a brief period before moving to more efficient communication methods, but they would continue producing waste heat and other byproducts as long as they exist. The James Webb Space Telescope, though primarily designed for other purposes, has the sensitivity to detect some technosignatures in the atmospheres of nearby exoplanets. Industrial pollutants like chlorofluorocarbons don't occur naturally and would be a strong indicator of technological activity. Take a breath. You are part of a civilization that looks outward, that builds telescopes, that sends messages into the void, hoping for an answer. You are living in the moment when humanity first truly grasps the scale of the galaxy and begins to search it for kindred minds. Whether we're alone or surrounded by silent neighbors, the Milky Way remains our home. A spiral of hundreds of billions of stars, spinning slowly through the dark, carrying us forward through time. The possibility that we might be alone is both terrifying and awe-inspiring. If no other intelligence exists, then consciousness is an incredibly rare and precious phenomenon. The universe would be unconscious except for us, unable to observe or understand itself except through human eyes. That would place an enormous responsibility on humanity. We would be the only way the cosmos knows itself, the only source of meaning and purpose in an otherwise indifferent universe. Our survival would become cosmically significant, and our extinction would leave the universe dark and unobserved once again. But the possibility that we're not alone is equally profound. Contact with another civilization, even detecting a simple radio signal, would be the most important discovery in human history. It would tell us that intelligence can survive its technological adolescence, that the great filter can be passed, that we're part of a larger community of minds scattered across the galaxy. For now, we wait and listen. The Milky Way turns slowly, its spiral arms sweeping through space, carrying billions of worlds, some surely capable of supporting life, perhaps some already hosting civilizations that are also listening, also wondering if they're alone. The silence continues. But the search goes on, driven by curiosity and hope, the belief that somewhere in this vast galaxy, someone else is looking up at their night sky, asking the same questions we ask, wondering if anyone is listening. The search has evolved considerably since the early days. Modern SETI programs can monitor millions of stars simultaneously across billions of frequency channels. The Breakthrough Listen initiative uses some of the world's most powerful telescopes and has surveyed thousands of nearby stars. The challenge is that we don't know what we're looking for. An alien civilization might use communication technologies we haven't imagined, or they might intentionally avoid broadcasting to avoid attracting attention, a scenario sometimes called the dark forest hypothesis. The famous WOW signal, detected in 1977, might have been exactly this: a brief, powerful signal that swept across Earth and was never seen again. Despite numerous follow-up observations, it has never been detected again and remains unexplained. Beyond listening for signals, astronomers search for technosignatures, the byproducts of advanced civilizations. Industrial pollution in planetary atmospheres, waste heat from massive energy consumption, megastructures around stars, or laser pulses for propulsion. The James Webb Space Telescope might find the first evidence of life in the chemical signatures of a distant world. And even if we never detect intelligence, finding any form of life, even microbes, would revolutionize our understanding, telling us that life is not unique to Earth. There's a rhythm to the Milky Way that astronomers are just now learning to detect. Not the slow rotation we explored, but something faster, more subtle. A pulse written in the birth and death of stars, suggesting our galaxy breathes in cycles we're only beginning to understand. Star formation in the Milky Way isn't constant. It surges and ebbs over tens of millions of years, creating waves of new stars that ripple through the disk. What drives these cycles? Several mechanisms work together. The galaxy's spiral arms compress gas clouds as they rotate, but the compression comes in pulses, creating periods of enhanced star birth. Interactions with satellite galaxies create periodic disturbances. Each time the Sagittarius dwarf passes through our disk, it sends ripples through the galactic plane, triggering star formation along its path. The Sun's motion through the galaxy exposes us to these rhythms. As we orbit, we pass through spiral arms, encounter stellar streams, and traverse regions of varying gas density. Each passage brings changes to our local environment. The disk doesn't remain perfectly flat either. It bobs up and down over time, creating vertical waves discovered by analyzing Gaia data. These oscillations might be triggered by satellite galaxies or dark matter subhalos disturbing the gravitational equilibrium. There are also hints of periodic bursts from the galactic center. The Fermi bubbles might be evidence of periodic activity from Sagittarius A, perhaps every few million years when the black hole devours a large gas cloud. But the galaxy's heartbeat doesn't echo only in light and gas. It pulses in the very bones of the disk itself. In October 2025, the European Space Agency's Gaia mission unveiled the most detailed map yet of these hidden waves. Colossal ripples that lift entire swaths of stars, hundreds of light-years above and below the galactic plane, like slow ocean swells rolling across a cosmic sea. One such wave, now called the Radcliffe Wave, stretches over 9,000 light-years, cradling the Orion Arm where our Sun resides. It wasn't born from a single event, but from a cascade. The Sagittarius dwarf's repeated passages, the gravitational tug of dark matter subhalos, even the gentle pressure of spiral density waves, all conspiring to make the Milky Way breathe. Picture it, every few 100 million years, as the Sun glides through the inter-arm void, it rides the crest of one of these waves. The disk thickens beneath us, gas clouds compress, and star formation flares in quiet bursts, new suns igniting like fireflies in the night. Then, as we descend into the trough, the pressure eases and the galaxy exhales, letting the disk flatten once more. This isn't chaos. It's choreography, a rhythm older than Earth itself, written into the motions of 100 billion stars. And we are tuned to it. The same waves that trigger star birth may have nudged the solar system's path, keeping us in the calm between arms where supernova blasts are rare and heavy elements arrive in measured doses. Astronomers traced one such ripple back nearly 1 billion years, finding it coincided with a spike in meteorite impacts on Earth, cosmic punctuation marks in the story of life's evolution. These waves don't just shape galaxies, they shape us. Every time the disk rises and falls, it adjusts the cradle in which our world rocks. Take a slow breath. And tonight, as the Milky Way turns above you, a silent wave rolls through the disk, lifting stars, cradling worlds, breathing with you. Feel it. The galaxy inhales, new suns ignite. It exhales, ancient ones fade. You are in the rhythm. Even the galaxy breathes. Even in its vast stillness, there are rhythms, cycles, patterns that repeat over timescales that dwarf human history but are measured and real nonetheless. We are products of galactic timing, born in a quiet moment between catastrophes, far enough from the violent center to enjoy stability, but close enough to inherit the chemical richness of billions of years of stellar evolution. And as we drift onward through these mysteries, we arrive at another layer of understanding, one that asks not just where life can exist, but where it's most likely to thrive. The Milky Way isn't equally hospitable everywhere. Just as planets have habitable zones where conditions are right for life, the galaxy itself has regions more conducive to the development of complex life. This concept, called the galactic habitable zone, suggests that life is most likely to emerge in a ring-shaped region of the galaxy, not too close to the center and not too far out in the sparse outer regions. The galactic center is a dangerous place. Supernova explosions are frequent, bathing nearby regions in deadly radiation. The high density of stars means close encounters are common, potentially disrupting planetary systems. And the central supermassive black hole, though currently quiet, has periods of intense activity that could sterilize nearby worlds. On the other hand, the outer regions of the galaxy are too sparse. There are fewer heavy elements, crucial for forming rocky planets and organic chemistry. Star formation is slower, meaning fewer chances for planetary systems to develop. The environment is metallically poor, as astronomers say, lacking the diversity of elements needed for complex chemistry. The galactic habitable zone lies in between, in the disk where our Sun resides, about 26,000 light-years from the galactic center. Here, conditions are just right. Enough heavy elements to form planets and life, but not so many violent events that life gets repeatedly sterilized. Research published by astronomers at institutions like the University of Washington suggests this habitable zone is roughly an annular ring, perhaps between 13,000 and 33,000 light-years from the galactic center. Our Sun orbits right in the middle of this zone, which might not be a coincidence. The concept of a galactic habitable zone adds another layer to the Fermi paradox. Even if many stars have habitable planets, only a fraction exist in the right region of the galaxy. This shrinks the number of potential sites for complex life, possibly explaining why we haven't detected anyone yet. But there are challenges to this idea. Life might be more resilient than we think, capable of surviving in a wider range of environments. Supernova explosions, while dangerous, are also sources of heavy elements necessary for planets. Without them, there would be no raw material for life in the first place. And the definition of habitable keeps expanding. We once thought life required an Earth-like planet in the habitable zone of a Sun-like star. Now we know life might thrive in subsurface oceans on moons like Europa or Enceladus, or in the atmospheres of gas giants, or even in the cold vacuum of space, riding on comets and asteroids. Each discovery expands the possible environments where life might exist, making the galaxy seem more crowded with potential, even as the silence persists. The concept also raises questions about the timing of life's emergence. The early universe contained almost no heavy elements. The first stars were made purely of hydrogen and helium, unable to form rocky planets or complex chemistry. It took several generations of stars living and dying to enrich the galaxy with the elements we rely on. Astronomers estimate that the galaxy became suitable for Earth-like planets about 8 to 10 billion years ago. Before that, there simply weren't enough heavy elements. This means complex life in the Milky Way is probably no more than 10 billion years old and likely much younger. Our solar system formed 4.6 billion years ago, relatively late in the galaxy's history. Life on Earth appeared quickly within a few 100 million years of the planet's formation. But it took billions more years for complex life to emerge, and intelligent life appeared only in the last few million years. If this timeline is typical, then most life in the galaxy might still be microbial. Intelligence could be extremely rare, even if simple life is common. This adds another dimension to those questions we pondered earlier about the great filter and the silence. Perhaps the answer isn't that civilizations destroy themselves, but simply that intelligence takes an extraordinarily long time to evolve, longer than most planets have existed. Alternatively, if Earth's timeline is unusually slow, then the galaxy could be full of ancient civilizations that emerged billions of years before us. These civilizations might be so advanced, so different, that we can't recognize their activities as technological. They might have moved beyond radio communication, beyond physical megastructures, into realms of technology we can't even imagine. They could be here, all around us, operating on scales or in dimensions we haven't learned to perceive. Take a slow breath. These are the mysteries that keep astronomers awake at night, the questions without answers, the silence that speaks volumes without saying a word. The position of our solar system within the galactic habitable zone might also protect us in other ways. We orbit the galaxy at a speed roughly matching the rotation of the spiral density waves that form the spiral arms. This means we spend most of our time in the relatively calm interarm regions, avoiding the violent star-forming regions within the arms themselves. This has been dubbed the local bubble concept, the idea that we exist in a relatively peaceful region of space, protected from many of the galaxy's dangers. The Sun's orbit is nearly circular, avoiding the more elliptical orbits that would take us repeatedly through spiral arms and closer to the galactic center. This stability may have been crucial for life's development on Earth. Long-term environmental stability, free from frequent catastrophic events, allowed life to evolve slowly and steadily from simple to complex forms. Not all solar systems have this luxury. Many orbit more erratically, passing through high-density regions more frequently, potentially exposing any planets to harmful radiation or gravitational disruptions. So perhaps the question isn't just whether planets are habitable, but whether their orbits keep them in safe regions long enough for complex life to develop. The study of exoplanet orbits combined with models of galactic structure is beginning to reveal which planetary systems might enjoy similar protection to our own. These systems, orbiting in stable circular paths within the galactic habitable zone, might be the best places to search for complex life and intelligence. And in this very moment, the James Webb Space Telescope has begun to map those protected pockets with unprecedented clarity. Just weeks ago, it imaged a distant star system in the Orion Arm. Our spiral neighborhood revealing a Jupiter-like giant shepherding inner rocky worlds through calm interarm space, its massive gravity shielding them from the chaos of denser regions. This super-Jupiter dances in a near-circular orbit, much like our own gas giants, creating a stable cradle where smaller planets can evolve without the constant threat of stellar close encounters or supernova blasts. These findings suggest our local bubble isn't unique. Similar oases dot the galactic disk, quiet bays where metallicity is high enough for complex chemistry yet low enough in violence for life to endure billions of years. In these sheltered zones, the galaxy whispers its gentlest secrets, worlds that might mirror Earth's long, patient journey from chemistry to consciousness. Perhaps the silence we hear isn't emptiness, but the soft breathing of countless cradles, each waiting for its own spark of awareness. Take a breath. You are not alone in the calm. You are one of many, held in the galaxy's quiet arms. And as we continue this journey through the Milky Way's secrets, we arrive at a question that ties everything together. The recognition that we are not separate observers, but participants, made of the same material, following the same laws, part of the same story that began 13 billion years ago. Every atom in your body has a history that spans the galaxy. The hydrogen in your water molecules was formed in the first few minutes after the Big Bang. The carbon in your cells was forged in the hearts of massive stars that lived and died billions of years ago. The iron in your blood was created in supernova explosions that scattered material across thousands of light years. You are not separate from the galaxy, you are made of it. This idea, popularized by Carl Sagan with his phrase, "We are made of star stuff," is literally true. Life on Earth depends on elements that could only be created in stars. Without stars living and dying, without supernovae enriching the interstellar medium, complex chemistry would be impossible. There would be no planets, no oceans, no life. The story of these elements is the story of cosmic evolution. In the beginning, the universe contained only hydrogen, helium, and trace amounts of lithium. These elements formed in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear fusion to occur. But these three elements alone can't make much. They're too simple. To build the periodic table, to create the diversity of atoms needed for planets and life, you need stars. Stars are cosmic furnaces, fusing hydrogen into helium in their cores. But in massive stars, the process doesn't stop there. As the core runs out of hydrogen, it contracts and heats, eventually becoming hot enough to fuse helium into carbon and oxygen. In even more massive stars, this process continues, creating neon, magnesium, silicon, and eventually iron. Iron is the end of the line. Fusing iron requires energy rather than releasing it, so once a star's core fills with iron, fusion stops. The core collapses catastrophically, triggering a supernova explosion that blasts the star's outer layers into space at a significant fraction of the speed of light. In the intense heat of the explosion, elements heavier than iron are created: gold, uranium, platinum, all forged in seconds and scattered across the galaxy. Remember that invisible skeleton we explored, the interstellar medium threading between the stars? This is how it becomes enriched, how the raw material for future worlds is seeded across light years. Each supernova writes its chemical signature into that cosmic web. Our sun is at least a third-generation star, possibly more. It formed from a cloud that was already enriched with elements from previous generations. The rocky planets, including Earth, condensed from the leftover material in the protoplanetary disk, building themselves from the ashes of long-dead stars. According to research from institutions like the Carnegie Institution for Science, the solar system contains material from dozens or even hundreds of different stars. Each element has its own history, its own journey through the galaxy, eventually coming together to form the world we inhabit. The calcium in your bones might have come from one supernova, the iron in your blood from another. The carbon that forms the backbone of every organic molecule in your body was forged in a giant star that died before the sun was born. You are a mosaic of stellar deaths, a collection of atoms that have cycled through the galaxy for billions of years, taking different forms, joining different structures, until finally coming together in the pattern that is you. This realization changes the way we think about ourselves. We're not isolated biological machines living on an insignificant rock. We're intrinsic parts of the galaxy's evolution, conscious expressions of cosmic processes that have been operating for 13 billion years. Every atom in your body has a history that spans the galaxy. The hydrogen in your water molecules was formed in the first few minutes after the Big Bang. The carbon in your cells was forged in the hearts of massive stars that lived and died billions of years ago. The iron in your blood was created in supernova explosions that scattered material across thousands of light years. You are not separate from the galaxy, you are made of it. This idea, popularized by Carl Sagan with his phrase, "We are made of star stuff," is literally true. Life on Earth depends on elements that could only be created in stars. Without stars living and dying, without supernovae enriching the interstellar medium, complex chemistry would be impossible. There would be no planets, no oceans, no life. The story of these elements is the story of cosmic evolution. In the beginning, the universe contained only hydrogen, helium, and trace amounts of lithium. These elements formed in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear fusion to occur. But these three elements alone can't make much. They're too simple. To build the periodic table, to create the diversity of atoms needed for planets and life, you need stars. Stars are cosmic furnaces, fusing hydrogen into helium in their cores. But in massive stars, the process doesn't stop there. As the core runs out of hydrogen, it contracts and heats, eventually becoming hot enough to fuse helium into carbon and oxygen. In even more massive stars, this process continues, creating neon, magnesium, silicon, and eventually iron. Iron is the end of the line. Fusing iron requires energy rather than releasing it, so once a star's core fills with iron, fusion stops. The core collapses catastrophically, triggering a supernova explosion that blasts the star's outer layers into space at a significant fraction of the speed of light. In the intense heat of the explosion, elements heavier than iron are created. Gold, uranium, platinum, all forged in seconds and scattered across the galaxy. Remember that invisible skeleton we explored, the interstellar medium threading between the stars? This is how it becomes enriched, how the raw material for future worlds is seeded across light years. Each supernova writes its chemical signature into that cosmic web. Our sun is at least a third-generation star, possibly more. It formed from a cloud that was already enriched with elements from previous generations. The rocky planets, including Earth, condensed from the leftover material in the protoplanetary disk, building themselves from the ashes of long-dead stars. According to research from institutions like the Carnegie Institution for Science, the solar system contains material from dozens or even hundreds of different stars. Each element has its own history, its own journey through the galaxy, eventually coming together to form the world we inhabit. The calcium in your bones might have come from one supernova, the iron in your blood from another. The carbon that forms the backbone of every organic molecule in your body was forged in a giant star that died before the sun was born. You are a mosaic of stellar deaths, a collection of atoms that have cycled through the galaxy for billions of years, taking different forms, joining different structures, until finally coming together in the pattern that is you. This realization changes the way we think about ourselves. We're not isolated biological machines living on an insignificant rock. We're intrinsic parts of the galaxy's evolution, conscious expressions of cosmic processes that have been operating for 13 billion years. NASA's Hubble Space Telescope and James Webb Space Telescope have captured images of stellar nurseries where this process continues today. Clouds of gas and dust collapse under gravity, forming new stars and planetary systems, each one containing the chemical legacy of the past. The Eagle Nebula, famously photographed by Hubble in the Pillars of Creation image, shows this process in action. Towering columns of gas, each light years long, are being eroded by ultraviolet radiation from nearby young stars. Within these pillars, new stars are forming, invisible at visible wavelengths, but glowing in infrared light. These newborn stars will eventually ignite, fusing hydrogen into helium, starting the cycle again. Some will live for trillions of years, barely changing. Others, the most massive, will burn bright and die young, exploding as supernovae within just a few million years and enriching the galaxy with another generation of heavy elements. Take a breath. The oxygen you just inhaled was created in a star billions of years ago, scattered by an explosion, drifting through space, eventually condensing onto Earth, cycling through oceans and atmosphere, absorbed by plants, released again, and now flowing through your lungs. Every breath connects you to the galaxy's history, a direct physical link to cosmic processes that dwarf human timescales. The study of stellar nucleosynthesis, the process by which stars create elements, has been one of astronomy's great triumphs. Beginning in the 1950s, physicists like Fred Hoyle, William Fowler, and Margaret Burbidge worked out the details of how stars could create all the elements we observe. Their work, published in a landmark paper in 1957, showed that stars are the primary source of carbon, nitrogen, oxygen, and most other elements. Later, research refined these models and discovered additional processes, like the R process, which creates roughly half of all elements heavier than iron in neutron star mergers. The detection of gravitational waves from merging neutron stars in 2017, combined with observations of the electromagnetic afterglow, confirmed that these violent collisions produce gold, platinum, and other precious metals. The gold in any ring or jewelry comes from neutron star mergers that occurred before the solar system formed. These neutron star mergers are extraordinarily rare and violent events. When two neutron stars spiral together, they're orbiting each other hundreds of times per second in the final moments before collision. The gravitational waves they emit carry away energy, causing the orbit to decay until the stars finally merge. The collision creates a kilonova, an explosion that briefly outshines an entire galaxy. In the intense heat and pressure, neutrons are crammed into atomic nuclei, creating elements far heavier than iron. Gold, platinum, uranium, thorium, all the heavy elements that cannot be created in normal stellar fusion, are forged in these seconds of cosmic violence. The material is then blasted into space at a significant fraction of light speed, mixing with the interstellar medium and eventually being incorporated into new stars and planets. Every atom of gold on Earth, in jewelry, in electronics, in dental fillings, came from neutron star mergers that occurred billions of years ago in the primordial Milky Way. Even the lighter elements have stories. The hydrogen in your body is primordial, formed in the first few minutes after the Big Bang, when the universe was a hot, dense plasma. As the universe expanded and cooled, protons captured electrons to form neutral hydrogen atoms, the simplest and most abundant element in the cosmos. This hydrogen has existed for 13.8 billion years, cycling through stars, clouds, planets, and living things. The hydrogen in the water you drink has been part of countless structures, from interstellar clouds to comets to oceans to rain to the cells in your body. The oxygen you breathe was created in massive stars, fused from helium and carbon in cores heated to hundreds of millions of degrees. When those stars died, they expelled their oxygen-rich outer layers into space, where it mixed with hydrogen to form water molecules that eventually condensed onto Earth. The carbon that forms the backbone of every organic molecule in your body came from stars similar to our Sun, but more massive. In their final stages, these stars puff off their outer layers as planetary nebulae, beautiful shells of glowing gas that drift through space for thousands of years before dispersing. The nitrogen in your DNA, crucial for the structure of genetic code, was created through a different process called the CNO cycle, where carbon, nitrogen, and oxygen participate in a chain of nuclear reactions that convert hydrogen into helium while regenerating the carbon. This process operates in stars slightly more massive than the Sunday. The phosphorus in your bones and DNA came from the silicon-burning phase of massive stars, created in the final days before those stars exploded as supernovae. Phosphorus is relatively rare in the universe because its creation requires very specific conditions that only occur briefly in a star's life. The sulfur in your proteins, the chlorine in your body's salt, the potassium and sodium that enable nerve signals, all were created in stars and scattered by their deaths. You are a collection of elements with different histories, different origins, brought together by chance on a planet that happened to form in the right place at the right time. These discoveries have profound implications. They tell us that the elements necessary for life are widespread throughout the galaxy, distributed by supernovae and stellar winds, mixed into the interstellar medium and incorporated into new stars and planets. This means the building blocks of life are common. Every star-forming region contains carbon, nitrogen, oxygen, and phosphorus. Every planetary system has access to the chemistry needed for organic molecules. If life is rare, it's not because the ingredients are missing. It must be because some other factor, the right conditions, the right timing, the right combination of circumstances, is difficult to achieve. But the mere fact that the ingredients exist everywhere is encouraging. It suggests that the galaxy is full of potential, countless worlds with the raw materials needed for life, waiting for the right conditions to kindle it into existence. The abundance of elements varies throughout the galaxy. Stars near the galactic center, which formed more recently from gas enriched by many previous generations of stars, tend to be more metal-rich. Stars in the halo and outer regions, which formed earlier from less enriched gas, are metal-poor. Our Sun sits in a sweet spot, with a metallicity that's roughly average for stars in the galactic disk. This metallicity was crucial for the formation of rocky planets. A star with too little metal cannot form substantial rocky planets because there isn't enough solid material in the protoplanetary disk. A star with too much metal might form planets that are too large, becoming mini-Neptunes rather than Earth-like worlds. The Sun's metallicity suggests it formed from gas that had already been enriched by at least one, probably several generations of stars. The supernova explosions that created the heavy elements in your body occurred before the solar system existed, perhaps hundreds of millions of years before, giving the enriched material time to mix thoroughly with the interstellar medium before being incorporated into the solar nebula. Some of those elements preserve traces of their origins. Certain isotopes, varieties of elements with different numbers of neutrons, can only be created in specific types of events. By measuring isotope ratios in meteorites, scientists can identify the contributions from different sources: red giant stars, supernovae, neutron star mergers, and even cosmic rays. This cosmic archaeology reveals that our solar system incorporated material from many different stars, each contributing different elements and isotopes. We are not descended from a single stellar ancestor, but from a whole community of stars that lived, died, and enriched the galaxy before the Sun was born. The connection between humans and the galaxy goes deeper than just atomic composition. The laws of physics that govern stellar fusion are the same laws that govern chemistry, biology, and consciousness. We are not separate from the physical universe. We are expressions of it, patterns that have emerged naturally from the same processes that create stars and galaxies. This unity is both humbling and exhilarating. It means we belong here, not as alien intruders on an indifferent world, but as natural outcomes of cosmic evolution. The galaxy has been building toward complexity for billions of years, and we are part of that story. Galactic archaeology, the study of stellar ages and chemical compositions, reveals this deep history. By analyzing the light from ancient stars, astronomers can determine when and where they formed, what elements they contain, and what generation of stellar recycling they represent. The oldest stars in the Milky Way, found in the halo and globular clusters, are metal poor. They formed when the galaxy was young, before many generations of supernovae had enriched the interstellar medium. These ancient stars are almost pure hydrogen and helium, with only trace amounts of heavier elements. As time passed and more stars lived and died, the galaxy's metallicity increased. Each generation of stars formed from gas slightly richer in heavy elements than the last. By measuring stellar metallicity, astronomers can estimate a star's age and trace the chemical evolution of the galaxy over billions of years. Our Sun, with its solar metallicity, represents billions of years of this enrichment process. The elements it contains, and that we're made of, required countless stellar generations to accumulate. We are late arrivals in the galaxy's story, beneficiaries of eons of stellar alchemy. Some of the carbon atoms in your body might have been forged in a red giant star 8 billion years ago. The oxygen you breathe might come from a supernova that exploded 6 billion years before the Sun formed. The iron in your hemoglobin could have cycled through 3 different stellar generations before finally being incorporated into Earth. Each atom has traveled unimaginable distances, spent billions of years drifting through the interstellar medium, been part of multiple star systems, and finally arrived here, in you, arranged in a pattern complex enough to contemplate its own origins. As astrophysicist Neil deGrasse Tyson once said, "We are not just in the universe, we are of the universe." And in the quiet of this November night in 2025, as the James Webb Space Telescope peers deeper than ever before, we glimpse the next chapter of that same alchemy. Just months ago, it captured a newborn star in the Large Magellanic Cloud, one of our galaxy's companions, surrounded by ice grains laced with complex carbon molecules, methanol, ethanol, acetic acid, frozen relics of chemistry that will one day rain onto worlds yet unborn. These aren't distant curiosities. They're the same ingredients that drifted through our own solar nebula, the same atoms that would later form the first oceans, the first cells, the first breath. The galaxy isn't finished with us. Every supernova still writing its signature, every neutron-star collision still forging gold, every quiet fusion in a red giant's heart is part of the same unbroken chain that began with the first light and now flows through your veins. You are not just made of the past. You are the Milky Way's living present, a fleeting arrangement of stardust that, for one brief moment, knows it is home. Take a slow breath. The story continues inside you, above you, forever. As we approach the end of this journey through the Milky Way's secrets, one final realization emerges, perhaps the most beautiful of all. The recognition that the galaxy is not just our home, but our origin, our context, and ultimately, our destiny. And so we return to where we began, drifting through starlight, held by a galaxy that keeps its secrets even as we uncover them one by one. We've learned that we live in a spiral we couldn't see for millennia, that a massive black hole anchors our galaxy's heart, that we're slowly consuming our neighbors, that most of our mass is invisible, that an intricate web of gas and fields threads between the stars, that the galaxy might be full of silent neighbors, that only certain regions can host life, and that we ourselves are made from the galaxy's atoms, recycled and reformed over billions of years. Each secret revealed raises new questions. Each answer opens new mysteries. The Milky Way is 100,000 light-years across, containing hundreds of billions of stars, trillions of planets, and clouds of gas that stretch farther than you can imagine. Yet it's just one galaxy among trillions, an ordinary spiral in an ordinary region of the universe. But to us, it's everything. It's home. Every element in your body was forged in stars that lived and died within this galaxy. The calcium in your bones, the iron in your blood, the carbon in your cells, all were created in stellar furnaces, scattered by supernovae and later condensed into the planet where you now rest. You are made of the Milky Way. You are not separate from it. You are its atoms, arranged in a pattern complex enough to look back at itself and wonder. As you close your eyes tonight, remember that you're not lying still. You're moving at 514,000 miles per hour, carried by a spiral arm in a galaxy rotating so smoothly you feel only peace. Above you, hidden by daylight or clouds, the Milky Way stretches across the sky, a pale river of light, each point a sun, perhaps with worlds, perhaps with others looking back, wondering if they're alone. The galaxy keeps its secrets gently. It doesn't reveal everything at once. Each generation discovers something new. Each telescope peers a little deeper. Each question answered births new mysteries. And perhaps that's the greatest secret of all, that the wonder never ends, that no matter how much we learn, the galaxy remains vast, beautiful, and strange. The rotation continues, unbroken since the beginning. The spiral arms sweep through space, carrying their cargo of stars and planets. The dark matter halo holds everything together with invisible hands. The interstellar medium flows and cycles, birthing new stars from the ashes of old ones. And somewhere in all this motion, on a small rocky planet circling an ordinary star, consciousness has emerged, capable of understanding what it's part of. We have mapped the spiral from within. We have measured the black hole at its heart. We have identified the dark matter that holds it together. We have traced the chemical evolution that makes life possible. And we have begun to search for others who might have done the same. But for all our knowledge, the galaxy remains mysterious. We don't know what dark matter is. We don't know if we're alone. We don't fully understand how galaxies form or why they look the way they do. We don't know what the far future holds, what will happen when Andromeda arrives, or whether humanity will still exist to see it. These unknowns are not failures of science. They're invitations, calls to future generations to keep looking, keep questioning, keep exploring. The Milky Way has more secrets waiting, and we've only just begun to uncover them. Take one last slow breath. Feel the stillness. Know that you are part of something ancient and ongoing, a spiral of starlight that began billions of years before you and will continue billions of years after, carrying your atoms forward into new configurations, new worlds, new mysteries. The Milky Way's secrets are yours to hold tonight, not as answers, but as quiet companions, whispers from the cosmic dark, reminding you that you are both infinitely small and infinitely connected. When you wake, you'll still be spinning through space at 500,000 miles per hour. The galaxy will still be turning, slowly, patiently, carrying you forward. The stars will still shine, even if you can't see them. And the mysteries will remain, beautiful and distant, waiting. Thank you for drifting through these mysteries with me tonight. If this journey brought you even a moment of peace, a gentle like or subscribe means the world. And please, if you're willing, leave a comment telling me where you are tonight and what time it is. I love knowing these quiet stories reach across the planet, finding listeners in every corner, all of us looking up at the same galaxy, wondering together. Now rest. Let the stars turn above you. Let the galaxy carry you gently into sleep. Sleep well, stardust. The spiral holds you and always will. And in that quiet embrace, remember, every night you fall asleep beneath this same river of light, the Milky Way is still writing its story one star at a time, one breath at a time, one dream at a time. Your heartbeat, soft and steady, echoes the slow pulse of a galaxy that has never stopped turning, never stopped holding you. Close your eyes now. The spiral is still here. You are still home.